I gotta ask you, what the heck is 3IATLAS?
This is a visitor, an intelligent visitor from another solar system. That means there's extraterrestrial intelligence involved. It means we are being visited. Well, I'll put my money on the bet that there is intelligent life throughout the galaxy.
Hey, stop what you're doing right now, because something just left our solar system, and nobody is talking about what it actually did here. On December 19th, 2025, an object the size of a small mountain passed Earth at a distance of roughly 270 million kilometers. And the second it cleared us, it hit the gas. Not a slow drift, not some random tumble. It accelerated hard, like it had finished a job and punched the throttle to get out. And you know what should have happened? It should have exploded, torn itself to pieces, because 1 kilometer wide chunks of ice and rock don't generate that kind of thrust without ripping themselves apart. That's physics. That's not opinion. But here's the thing. It didn't explode. It's still whole, still moving, still perfectly intact. Everyone's calling this a flyby. The news, NASA's public statements, every article you'll read. Historic moment, interstellar visitor. Isn't space amazing? Let's all move on. Except something happened that nobody wants to talk about directly. Quick pause before this gets even stranger. If you're into this kind of no short butts, follow the physics breakdown. Take a second to like the video, subscribe to the channel, and hit the notification bell so you don't miss what comes next. It's free, it really helps the channel, and the algorithm tends to reward curiosity. We genuinely appreciate the support. This thing came in on a precise trajectory past us at an optimal distance. Not too close, not too far. And the moment it cleared Earth, it started burning velocity. Not slowing down, speeding up. And the acceleration means it's moving faster than Voyager 1 right now, faster than Voyager 2, faster than anything humanity has ever launched into deep space. Voyager's been flying since 1977, almost 50 years, and this object is already leaving it in the dust. Think about that. Our fastest probe, our proudest achievement in interstellar exploration, getting outrun by something that wasn't supposed to be able to do this. So now you've got a 1 kilometer object generating impossible thrust, maintaining structural integrity it shouldn't have, hitting speeds that embarrass our best engineering, and doing all of this immediately after its closest approach to Earth. Not before, not during some random point in its journey, right after passing us, like it had a pickup scheduled. I want to hear your take here. When timing lines up this cleanly, do you still read it as coincidence? Or does it cross into something that deserves closer scrutiny? Let us know in the comments. We really do try to read as many as possible, especially thoughtful, constructive ones. And when we can, we reply or use strong points as fuel for future episodes. Now, I know what you're thinking. Coincidence, right? Just weird comet behavior we haven't seen before. We've only studied a handful of interstellar objects. Maybe this is normal for where it came from. Maybe their ice is different. Maybe we just don't know enough yet. And look, I'm trying to be fair here. I really am. Science is about ruling things out, not jumping to conclusions. But then Avi Loeb, Harvard astronomer, former chair of the astronomy department, the guy who won't stop talking about Oumuamua possibly being artificial, comes out and says something that changes the entire frame of reference. He says, these objects aren't just visitors, they're freight trains, natural interstellar transport systems that cross between star systems whether we're paying attention or not. And here's his proposal. Forget building slow probes that take tens of thousands of years to reach another star. Why would you do that when nature is already providing fast-moving objects that make the trip regularly? You hitch a ride, attach your payload, let the object do the work. He's literally suggesting humanity should use passing interstellar objects as cargo ships, stick scientific instruments on them, time capsules, messages, biological samples, DNA seeds, whatever you want preserved and transported. And the math works. At 60 kilometers per second, you're reaching deep interstellar space 20,000 years faster than Voyager. That's the difference between your great-great-great-grandkids maybe seeing results and having no realistic hope at all. So Loeb says, we could do this. We could send things outbound on these natural carriers. And that's when the question flips. If we could do it with our limited technology, right now, today, why wouldn't someone else have already done it? Why wouldn't a civilization with a head start, with better tech, with more time to plan, use these exact same objects as their logistics network? You send the transport toward a target system. It arrives, it does whatever it needs to do, then it leaves, picks up speed, and heads to the next stop. That's not a flyby, that's a route, a shipping lane. And if that's what we just watched, then the question isn't what is this thing? The question is, what did it take with it when it left? Or worse, what did it leave behind? Because here's where the data gets really uncomfortable. The object has been shedding material. That's confirmed. Fragments ejecting off the main body as it moves. And the official explanation is outgassing. Ice turning to gas. Chunks breaking loose. Normal comet stuff. Except the math doesn't work. The amount of thrust this thing is generating through gas alone would require it to lose so much mass that it should be visibly fragmenting, crumbling, falling apart. It's not. It's intact. So if gas isn't providing enough thrust, what is? This is another moment where your reasoning matters. Do fragment ejection models feel sufficient to you, or do you think the explanation still leaves gaps? Share how you're weighing the physics. We really value careful, detailed comments. We read them closely, and sometimes they directly shape what we investigate next. New models suggest fragment ejection, solid pieces being thrown off the main body. That works better mathematically. Fragments carry more momentum per unit than gas does. More efficient. You can generate the thrust we're seeing without destroying the object. Okay, fine. Fragments, ice chunks, debris trailing behind it. Solar wind sweeps it away. No big deal. But here's the thing nobody's saying out loud. Those fragments aren't just drifting randomly. Physics says if you eject something at the right velocity, at the right angle, during a close planetary flyby, you can park it, put it into orbit, make it stay. Most fragments would shoot off into space. Solar wind, radiation pressure, gravity interactions, they'd disperse, but not all of them. Some, if ejected with precision, could decelerate into bound or semi-bound orbits around Earth, or into positions where they'd be gravitationally stable for years, and we would never see them. Our asteroid detection systems are optimized for one thing: kilometer-scale objects, planet killers, the stuff that wipes out cities or ends civilizations. That's what gets funding. That's what gets telescope time. That's what makes headlines and justifies billion-dollar programs. Big rocks, big threats. Meter-scale objects in high orbit, that's a different story. Dark, cold, non-reflective, no dramatic impact scenario, no extinction narrative. We're not set up to find those. Not technologically, not institutionally, and not politically. They don't glow. They don't reflect much light. They don't cross Earth's orbit in obvious ways. They don't trigger automated alerts. They don't look dangerous enough to justify expensive tracking campaigns. They fall into a blind spot, a gap between planetary defense and satellite monitoring. They'd be invisible, not because they're impossible to detect in principle, but because we're not looking for them in practice. And they could be up there right now, not approaching, not departing, just sitting, and we'd have no idea. So ask yourself this: if you were designing a system meant to quietly place objects near Earth without drawing attention, where would you put them? High Earth orbit, way beyond satellite traffic, is the first answer. Past geostationary orbit, past GPS constellations, past the regions we actively manage and catalog, out where objects can drift for years without interference, minimal collision risk, minimal observation. Then there are the Lagrange points, gravitationally stable regions where the forces of Earth and the Sun balance out just enough that objects can remain parked with very little energy input, L4 and L5 especially, 60 degrees ahead of and behind Earth in its orbit. Trojan points, natural collection zones. We barely monitor those. They're not empty. We know that. Dust accumulates there. Small asteroids collect there. But they're not a priority. They're quiet regions. Nothing dramatic happens there. No one expects anything interesting, which makes them perfect. Or you go one step further and put objects into Earth-like heliocentric orbits. Same path around the Sun, same speed, slightly offset, always nearby, always hidden in the glare, always moving with us instead of toward us. They shadow our trajectory, never close enough to be noticed, never crossing paths dramatically, just quietly keeping pace. All three options share the same properties: stable, long-term, unmonitored, and critically, they don't require continuous propulsion. Once something is there, it can stay there for years with minimal intervention. Long-term parking spots. And before you say, there's no evidence for any of this, hold on, because in the weeks around closest approach, things started happening that don't fit the normal pattern. Atmospheric reports began coming in, not from one region, not from one country, globally. Reports of slow-moving meteors. Orange-colored, traveling at shallow angles across the sky, almost parallel to the ground. And the timing was wrong. These weren't part of any known meteor shower. They didn't line up with predicted debris streams. They weren't associated with known comet trails. They appeared outside expected windows. Slow meteors are weird by themselves. Most meteors slam into Earth's atmosphere at extreme speeds, 30, 40, 50 kilometers per second. They're falling toward the sun. Earth just happens to be in the way. High speed, deep entry angle. Bright flash. Gone in seconds. That's normal. But slow meteors, ones moving at speeds comparable to Earth itself, that tells you something important. They weren't falling in from deep space. They were already here, already in similar orbits, already traveling alongside us. Then something changed. Then they entered the atmosphere, like they were dropped off. That doesn't automatically mean intent. There are natural explanations: orbital perturbations, minor gravitational nudges, atmospheric drag at high altitudes. But when you see multiple slow entries clustered in time around a specific event, you start paying attention. Then you've got the satellite reports. GPS disruptions during the flyby window. Nothing catastrophic, no systems failing outright, no satellites falling from the sky, but anomalies, unexpected orbital drag, resistance where there shouldn't be any at those altitudes. Satellites experienced slight changes in behavior, subtle, easy to explain away individually, but the timing lines up. Now, I need to be honest here. There's no confirmed causal link. Space weather was active. Solar maximum is ongoing. The sun is throwing radiation and charged particles at us constantly. Satellites glitch, GPS hiccups. This happens all the time. Engineers deal with this every day. But the timing was specific. The distribution was global, not localized to one region, and the frequency of anomalies spiked during the flyby window, then dropped off afterward. Correlation isn't causation. Everyone knows that. But when you stack coincidences, trajectory optimization, fragment ejection, atmospheric anomalies, satellite disruptions, your brain does what it's evolved to do. Pattern recognition kicks in, and you start asking whether these things are actually independent. Could be wrong, absolutely could be wrong, but the hypothesis predicts exactly this kind of noise, exactly this kind of low-level disturbance. Nothing dramatic, nothing undeniable, just enough to notice if you're paying attention. And that brings us to the radio silence. Because if this thing was artificial, if it was controlled, if it was part of some larger system, surely it would be broadcasting, right? The Allen Telescope Array watched it for 7 hours across a frequency range from 1 to 9 gigahertz. That's a wide sweep. That's where you'd expect intentional signals. That's where SETI listens. They found nothing. Well, not exactly nothing. They detected 74 million signal hits initially. That sounds dramatic until you realize that's just background noise, human technology, natural sources, random interference. After filtering, 211 candidates remained. After analysis, 0 were worth following up on. Total silence. Case closed. Except the upper limit they calculated is interesting. If the object was transmitting during those 7 hours, it was doing so at a maximum power between 10 and 110 watts. That's a household light bulb. You can't shout across interstellar space with a light bulb, unless you're not shouting. If this is a transport mission, broadcasting in all directions is inefficient. It wastes power. It advertises your position. It alerts every observer in range. It's the worst possible communication strategy. You don't shout into the void. You aim. Tight beam. Narrow focus. Directed transmission aimed at a specific receiver. Everyone else hears silence. Earth was never the audience. And here's where it gets even stranger. The object is heading toward Jupiter. March 16th, 2026. Closest approach, 53 million kilometers. And it doesn't need Jupiter. It's already moving fast enough to escape the solar system. It's already past solar escape velocity. Any gravity assist from Jupiter is a bonus, not a requirement. So why line up the trajectory? Because Jupiter isn't just big. It has the strongest magnetic field in the solar system. Absolutely massive. Enormous magnetosphere extending millions of kilometers into space. Magnetic fields interact with charged particles. They can amplify radio emissions, focus them, shape them, act like a natural antenna on a planetary scale. If you wanted to send a signal out of the solar system, if you wanted to boost transmission strength without carrying massive onboard power sources, that's where you'd do it. You use the planet, and that's where it's going. March 16th isn't just another observation date, it's a test. A binary one. Either This thing behaves exactly like a rock governed purely by gravity, inertia, and outgassing? Or it does something rocks don't do. And if it does, everything changes. Because natural objects don't course correct twice. Once is an anomaly you can argue about for decades. Twice is control. Twice is intent. Twice is technology operating according to plan. And that's why we're watching. Not because we're curious, because we need to know. Because if this was a random rock, then science just got a lot more interesting. But if this was a scheduled stop, then we weren't alone in our own neighborhood. We were part of something larger, and we didn't even realize it. If you want to keep following this as it unfolds, make sure you're subscribed, leave a like, and turn on the notification bell so you don't miss the next update. It doesn't cost anything, but it's the best way to support the channel and stay ahead of whatever happens next. And if you know someone who obsesses over space anomalies or deep space physics, sharing this